Yo, what's up, Sci Fam? It's your boy Nickel, and today we're going to investigate and hopefully understand a little bit better acids and bases. So you can see we're going to define acids and bases. We're going to look at some strong acids and weak acids, some strong bases and weak acids. We'll also understand what the pH scale is and discuss how carbon dioxide falls underneath one of the categories of acids or bases. So let's begin by defining what an acid is. Now, there's several different definitions, but for right now, we're just going to keep it simple. And for an acid, we're going to define an acid as something that is going to involve hydrogen ions. So an acid is something that is going to donate hydrogen ions. Now, if I say an acid is a hydrogen ion donor, we really have to look at some examples to understand what this means in a solution. When we talk about an ion is something that has lost or gained an electron. So if we look at a hydrogen ion, we need to use the capital letter H because we're looking at the element hydrogen. And in this example, if it's a hydrogen ion, it lost an electron. Since it lost the electron, an electron is a negative charge. So if it lost a negative charge, it's now a positive ion. So an acid is something that donates a hydrogen ion into a solution. So our first example we're going to look at here is hydrochloric acid. You might have heard of this acid before, HCl, meaning that it has hydrogen and chlorine bonded together to make hydrochloric acid. When you put hydrochloric acid into water, water's chemical formula is H2O. So when hydrochloric acid is in water, it actually will dissolve. And the bond that's between hydrogen and chlorine will disassociate because this hydrogen is going to be attracted to the water. And it's going to bond to the oxygen in the water, giving the oxygen an extra hydrogen. So when you have hydrochloric acid in water, it ends up forming hydrogen ions, which sometimes will connect with H2O and form H3O. And we put a plus there as well because this hydrogen ion is still missing the electron, so it carries that plus charge. And then the chlorine just ends up kind of on its own, but it holds on to the electron that it stole from hydrogen, so it has a negative charge on it. You see, hydrogen and chlorine were sharing electrons. And so these two right here were shared, and that's where we draw the bond. When hydrogen left without its electrons. Let me try that without getting the highlighting in there. Hydrogen leaves without the electrons, meaning that chlorine gained an electron here, and hydrogen is missing one. So therefore, since it's missing a negative electron, we put the plus with the hydrogen, and the chlorine gained a negative electron, so we say it's a negative. So when hydrochloric acid is in water, it forms H3O+, but it's really floating hydrogen ions and floating chlorine ions. The hydrogen is the H+. So HCl, or hydrochloric acid, is donating, or it creates hydrogen ions that can then be donated to either the water or other things that are in the solution. So this is an example of a strong acid. And it's a strong acid because that hydrogen is happy to leave the chlorine. And the chlorine is happy to let the hydrogen go because it has both of its, because it has a full 8 electrons in its outer shell, a full octet. Now, let's go from having a strong acid to a weak acid. And this weak acid that we're going to look at is acetic acid. Acetic acid is also known as vinegar. So when you put vinegar into water, the acetic acid acts like a acid. That's why we say it's an acid, acetic acid. So it's going to actually donate this hydrogen ion. Some of those hydrogen ions might create H3O, but basically they're going to float around and leave the rest of this molecule from where it was attached. So when you put acetic acid in water, what we end up with is CH3COO. Now, it keeps the electron from that hydrogen ion, so therefore it has a negative charge. Since the hydrogen leaves its electron behind, then we just have a hydrogen ion with the plus. So again, acetic acid is going to donate those hydrogen ions. Acids are any type of substance that is going to donate hydrogen ions. Now, this acetic acid is considered a weak acid because with this CH3, COO minus sitting around, it actually wants to clump back together sometimes. So when we draw this reaction to show what happens with a weak acid, some of the stuff, some of the reactants, or some of the products, some of the stuff that's created at the end actually goes back into forming more reactants. And so it kind of, although some hydrogen ions are donated, some of those hydrogen ions clump back up with the original, with the other part of the product to make the original reactants. So anytime that this hydrogen ion can float around in the solution, it's going to be an acid. If it floats around freely and is happy to leave the other part of the molecule, then it's a strong acid. And if it kind of rejoins and is kind of unsure whether or not it's going to stay or go, then it's a weak acid. All right, let's now transition to look at bases. Bases are basically the opposite of an acid. So we're still going to be looking at hydrogen ions. And those are those H plus ions. So instead of giving out hydrogen ions, a base is something that will look for and grab a hold of and make bonds with hydrogen ions. So therefore, we would say that these are hydrogen ion acceptors. Acids are donors, bases are acceptors. So, as some examples down here, let's first look at NaOH. This is known as sodium hydroxide. When sodium hydroxide is placed in water, this OH molecule and this sodium molecule are going to separate from each other. The sodium is going to leave behind one of its electrons. So therefore, in the products, we're going to end up with OH minus because it gained an electron, and the sodium left an electron behind. Since it left a negative behind, it's now positive. So when we have sodium hydroxide in water, it ends up forming sodium ions and hydroxide ions. And you can see a hydroxide ion is almost water. What does it need to form water? It needs an H plus in order to form water, and then it will become H2O. You see, so when sodium hydroxide is placed in water, these OH molecules, these hydroxide portions of the molecule, these hydroxide ions, are looking for an H plus. So they want an H plus really, really bad. So they have an open spot. They are ready to accept hydrogen ions. So when sodium hydroxide is placed in water, these hydroxide ions, the negative OH, is looking for a hydrogen to connect with so that it can equalize. So when this happens very easily, like with sodium hydroxide, this is called a strong base. So you can probably guess our next example is going to be a weak base. And the same thing's going to happen. One of these hydrogen, one of the atoms of hydrogen here in our ammonia is going to leave the ammonia molecule. And this is going to happen when it's placed in water, in H2O. And when this does happen, it actually is going to end up forming NH4. So actually I was wrong about that. Not that one leaves here, because that would have been an acid. It's going to gain a hydrogen ion, so it's going to accept it, and it's going to leave behind some hydroxide ion as well. So again, this hydroxide ion is looking for some other hydrogen ions to connect with, but every once in a while it steals one back from the ammonium that ends up being formed. It steals one of those hydrogens back from it. So sometimes it goes backwards and it goes back into the NH3, and then it goes forward and it creates NH4, but sometimes that hydroxide ion joins with the OH again to form water, and it ends up going back to the reactant. So sometimes the products don't stay products, they go back into the reactants. So we would call this a weak base, because even though it will accept some hydrogen ions, sometimes it goes back to its more stable form. So that would be a weak base. So in summary, a base is something that accepts hydrogen ions, and a lot of times you'll see that there's this hydroxide ion And this hydroxide ion is looking for a hydrogen ion. For acids, they are going to donate hydrogen ions, and so you're going to usually see the H plus there in the products, or sometimes you'll see it as H3O plus. All right, so in order to measure if something's a weak base or a strong base, there's a scale known as the pH scale. Now that we've discussed what an acid and a base is, perhaps you now understand that this is telling us basically how many of those hydrogen ions are in a solution. So pH is something that measures the acidity or the basicity. The basicity or the acidity, how acidic or how basic a solution is. And a solution is going to be something that's in water. So when you put an acid in water, it's going to have a lot more of those H plus ions. If you put a base in water, it's going to take more of those H plus ions away. It's going to bond with them. So the way that the scale works is it has 0 on one end and 14 on the other. 7 then is right in the middle. So 7 is what we would call something that is neutral, meaning it doesn't accept or donate those hydrogen ions. It's in that neutral state. It's not going to accept or donate. As it donates more and more, it becomes more acidic, and more acidic is closer to 0. So on the 0 to 7 side of our scale are our acids, and on the 7 to 14 side of the scale, this is where our bases are. So if you were to measure a solution and it had, let's say, 8.1 pH, which is the average pH of the ocean, then it would be more of a base. If you were to measure something like a lemon, and a lemon can be pretty darn acidic, I'm not sure what the actual pH would be, but be somewhere in maybe like the 2 range or even the 3 or 4 range, that's going to be something that's an acid. So the bigger the number, the stronger the base. The smaller the number, the stronger the acid. In the middle means that it's neutral. But every time you change even one number from like 7 to 8 or 8 to 9 or 9 to 10, each change of 1 pH is equal to a 10 times increase in the number of H plus ions. So if you have an acid, let's say the acid is a 1 on the pH scale, and you go up to a 2 on the pH scale, it means that it's less acidic by 10 times. And if you were to go up to a 3 on the pH scale, that means that that acid is 100 times less acidic than the 1 was, and so on. You would add a 0 each time because each increase is 10 times difference. All right, so let's talk about how this relates to the carbon cycle, specifically by looking at carbon dioxide. You see, carbon dioxide in our atmosphere dissolves in water. When it dissolves in water, it forms H2CO3, which is carbonate. Now, this type of molecule here, the H2CO3 molecule, when it's in water, it actually is going to act like an acid. It's going to donate some of its hydrogen ions, and it's going to leave by some HCO3 minus is the name of that, is what we end up with here. HCO3 minus, we lost a hydrogen ion from that. That hydrogen ion is now being donated to other things. So therefore this is considered a weak acid. So the weak acid forms those H plus ions, the hydrogen ions, which then bond with the carbonate atoms, or with the carbonate ions. And the carbonate ions are CO3 2 minus. These carbonate ions are things that float in seawater. These things floating in seawater, when they attach to the hydrogen ion, they no longer are available for shellfish. So shellfish have less of these carbonate ions available, which means that they can't build their shells as well, which means that they can't survive as easily. So when CO2 dissolves in water, this H2CO3 forms, which is a weak acid. The weak acid prevents the carbonate ions being available to the shellfish, which means it's harder for them to live. So as we have more CO2 in the atmosphere, more of it will dissolve in the water, making our oceans more and more acidic. This can also dissolve the shells of the organisms, and It reduces the amount of resources available for them to build their shells. Hey, now you know how acids, bases, and pH relate to the carbon cycle.